Okay, well, um, the next topic I wanted to talk about is just, I would call it pointer arithmetic. So I'm going to make another directory. I'm going to move the pointers intro. Actually, I guess I'll use pointer struct star, move that here. So just keep building on this. Okay, so I'm going to create another method, and we're going to call this one void um, uh, arithmetic example. Okay, so this time I'm going to create a double. Star dp, a double reference, and I'm going to set that equal to a new double with the initial value of 42. I'm going to create a second double reference, ep, and I'm going to set that equal to dp. I'm going to say star dp equals star dp plus 4200. And then I'm going to say cout star ep. Well, let's do a little bit more than that. Cout. We'll cout and dp, and give that a space there, and we'll get out and dp. We'll output dp, and we'll output star dp, star dp. Okay, and we're going to do the same thing for EP for all of this. Okay, so okay, cool. So now the question is, if I run this program, what do you expect to see when I run this program and these two cout statements execute? So if you think about this a little bit, we're going to see a couple of interesting things. So when I output ampersand dp, what I'm going to output is what is the location in the stack of arithmetic example for the reference dp, all right? So there's an address on the stack where the variable dp is located. There's also an address on the stack where the variable ep is located. So we're going to see two different addresses, all right? Now, when I say dp, what I'm saying, printing out dp, what I'm printing out is the location in the heap where this double was created. And since I set ep equal to dp, when I output ep, I will see the same location on the heap. When I say star dp, what's going to happen is I'm going to dereference that location on the stack, and I will get, sorry, that location on the heap, and I will get to the location in the stack, in the heap that has the value 42. So that should output 42. Since EP has the same location on the heap that DP has, I'm going to see the value 42 when this part of the cout statement, star EP, gets executed as well. All right, so let's try this. Oops, that didn't work because I forgot to execute it down here. All right, so let's take a look. So the address for DP on the stack frame is this, and the address for EP in the stack frame for the method is this. So these should be two different values because they're two different variables on the stack frame. However, the value for DP and the value for EP are the same. And when I dereference DP, I get 4242. And when I dereference EP, which is the same location on the heap, I get 4242. So that should all make sense. Kind of interesting to look at these two values here and think about how many bytes different they are, because this is a clue as to how many bytes are allocated for an address, right? This is FDD8, this is FDE0. So let's see. To get to E0 from D8, how many bytes is that? Well, if we add 8 bytes to D8, we'll get to E0. That means that every address in a C++ program is 8 bytes, which makes sense if you think about most modern computer architectures are 64-bit architectures. 8 bytes times 8 bits gives you 64 bits. So it makes total sense that these two addresses are 8 bytes apart because we need 8 bytes to hold the address of the variable DP, and 8 bytes on the stack frame to maintain the address for DP, and the same thing for EP. Now, I didn't quite say that right. We need 8 bytes to hold the address for the heap location for the double that we created. And so since we need 8 bytes, that's where there's a distance of 8 bytes between these two variables, which are supposed to hold address values on the stack. Just a few years ago, you would see not 8 bytes, but 4 bytes. And that's because we were using 32-bit architectures, which meant that addresses were stored in 32 bits or 4 bytes. All right, cool. So let's mess around with this a little bit more. First of all, do we have a memory leak here? I believe the answer is yes. We have a new here, so we're carving out some memory on the heap, but we're not doing a delete. So let's be a good doobie, all right? We're gonna delete DP and then set DP equal to null. Awesome. But what about EP? Do we need to delete EP? Huh, that's an interesting question. Let's try deleting EP. Maybe we do. It's null capitalized. Seems to be okay. Let's try running it with Valgrind. Oh, looks like we have an error here. Yeah, it looks like we've got an error, invalid free delete, and it looks like it's occurring on line 75 of main.cpp. So let's take a look. Here's how you get to a line: escape X, go to line, 75. Oh, well, of course, that's not very helpful. What line inside arithmetic? Line 68 inside arithmetic example. Escape X, go to line 68. So something around here is invalid. All right, I think that this delete's okay. This delete DP equals null. Let's comment the delete EP out and try running it again. Run Valgrind again. Okay. So things look pretty good here. There's no leaks, there's no errors. So that second delete is a problem. Now, why is that? Well, let's take a look. If we say delete DP equals null, what we're doing is we're deleting the chunk of memory that's associated with the double that was created right here, okay? So that part on the heap, that 42, that double that has the value 42, that is freed up for someone else to use that chunk of memory. If we try to delete EP, what's happening? Well, EP has the same address on the heap as DP because we made an assignment statement here. So in effect, we are trying to delete that chunk of memory again on the stack, on the heap. And that's an error because we've already freed it up. So that's an invalid delete. Now we could do this. Could put a comment there. So we're not deleting DP, we're deleting EP. We're going to have the same net effect. When I say delete EP equals null, that delete EP is going to get rid of the new double up here. And then we don't need to do the delete DP. And just to be nice and clean and tidy, I think I would probably set DP equal to null here as well. And we'll do a make. And we'll try Valgrind on that. All right, Valgrind's pretty happy as well. Let's go one more time back at our main.cpp. Okay, so the reason why I set DP equal to null is because DP is a reference to that double on the heap, which we just deleted. So we want to make sure DP and EP are both null so that there's no chance that we messed with that deleted reference. Because if we do that, we have that dangling pointer problem again. Okay, great.